Today we have Javier Martín, and he will be talking about momentum complexity correspondences. Please, Javier, you can start.
Okay, thank you very much, Sibyl, for all the organization. Okay, so I prepared some notes about this, but as you see, these are just a bunch of handwritten notes. So what I really like with these things is that just to do Blackboard talks, but since we can't in these times, well, I have to do this, but what I mean is that please interrupt me whenever you want, because I would prefer if this were more like a journal club to discuss things than a formal seminar. All right. So if you don't understand something, or even if you want to get stuck at the beginning and just not let me finish, for me, that's okay, as long as we discuss about something and we learn something. Okay, so I'm going to talk about this momentum complexity dualities or correspondences or whatever, which is some work that I've done with my former supervisor, José Luis Barbón, and another student, Martín-García. So it's going to be based on these three papers, which are basically on the same issue, just refining and developing the same idea further and further. And it's well, as you will see, it's a set of things that it's motivated on some crazy ideas from Leonard Susskind. You know that he is quite a provocative guy that has strange ideas in that and always has had them in the past. Many people laugh at him, but sometimes he turns out to be right. But actually, the work that we did is just work in general relativity. So even if you don't believe the motivations that drive us to do these calculations, you may be interested in just some computations in general relativity, because there's nothing more than that. Okay, so it's been now over 20 years that we have this awesome correspondence that we call ADS-CFT that tells us that just quantum gravity can be simply defined as a simpler theory that has no gravity as long as it is conformal, and that as long as this gravity lives on asymptotically anti-de Sitter space. And for these last 20 years, we have been basically computing the dictionary, which is the list of quantities that we know on one side and what we believe are the corresponding quantities on the other side. And one of the most interesting entries that we have in this dictionary, in my opinion, it was the realization that black holes, which are kind of a mysterious object, always have been from the point of view of general relativity, are something pretty simple in the dual theory, which is that it's just a thermal system, right? It's a kind of exotic thermal system, right? Because it's probably made of it's a soup of n=4 super mil particles or whatever, but it's still something that we more or less understand. So one of the big hopes, I think, in these years have been that this duality could help us to understand better these black holes. In particular, one big hope was that maybe the conformal field theory would tell us something about the interior of the black hole, or on the singularity, and which is the part that is most mysterious. And since this duality was initially developed by string theorists and particle physicists, I think people focused at the beginning a lot on quantities that they were used to, like maybe scattering amplitudes, operators, things like that. But after a while, they realized that maybe the quantities that one should look in this holographic duality, if one wants to learn about the black hole interior, are not really particle theory like quantities, but more quantum information quantities. So it turns out there's a very interesting chapter in the holographic dictionary that is devoted to quantum information. And what this chapter has told us along the last maybe 10 or 15 years is this suggestive slogan that entanglement builds a space, meaning that the emergence of a space-time in quantum gravity and the very connectivity of space-time, it's very tied to the structure of entanglement of the conformal field theory that is dual to. This has also been called the ER = CPR proposal, which is just another slogan saying basically the same, and of course has more concrete realizations, such as, for example, the celebrated Ryu-Takayama formula, which tells us that one can compute the von Neumann entropy of some region in a conformal field theory by means of a simple externalization procedure in ADAs, which is something very interesting and that has produced a lot of insights about gravity. For example, there has been people that has worked, for example, on proving energy conditions from this Ryuta-Kayanagi formula. There have been a lot of developments on the quantum on the black hole information problem, just based on these ideas. There's even proposals that maybe the Einstein equations could emerge from properties of entanglement entropy, with these papers of Van Rassong and so on. So a lot of developments have come from this idea. However, there are reasons to think that entanglement entropy by itself, or different measures of entanglement entropy, which has been the thing that has been most studied, is not enough to fully recover the structure of spacetime. Right? The dream would be that maybe just classifying all types of regions or all types of von Neumann entropies that one can compute, this could completely characterize the geometry. But this is not true, because these Ryuta-Kayanagi surfaces in general don't like black hole interiors. In particular, they don't like horizons, right? When one computes a Ryuta-Kayanagi surface and there is a horizon present, usually you see something like this picture, which is that the surfaces tend to just rest on the horizons, but they don't like to dive in. So it is hard to use these quantities as diagnostic tools for what happens behind the horizon. Even you can try even harder and do more exotic things, like, for example, taking an eternal black hole, which is due to some thermophile double, and just taking regions that are shared in both sides. Sorry.
This statement is only true for static black holes.
Yeah, sure.
So Kayanagi avoiding the crossing.
Sure. So, and actually, what I was going to say is that so sometimes the Ryuta-Kayanagi does enter, but usually it doesn't do it for so long. So usually it's some finite time thing. Like, for example, in this Haltman-Maldacena paper. So before what you consider thermalization time, it's true that there are some choices of regions that make Ryuta-Kayanagi surfaces to enter. But they don't do it for so long, so you're not allowed to explore the interior in full glory.
Typically, what happens is that if your boundary area grows a lot, then your Ryuta-Kayanagi surface pierces the horizon, but it typically bends into the past, and then sometimes it exits again. So it's a very peculiar thing. What happened? It's true that it typically escapes the origin because of this bending towards the past. So this is something that, well, in particular, Esperanza found. Okay, that was
So all this, what I meant is that they do enter sometimes, but it's not automatic to for example to explore the full interior. So this is connected, for example, to the problem of how do we reconstruct operators that live behind horizons. All right. So there is this whole procedure by this HKLL procedure that allows you to reconstruct operators in the bulk from operators in the boundary, and this whole thing is tied to what is the entanglement weight of this region, right? And usually the interior of the black hole is not in the entanglement weight of anything. It's really hard to reconstruct operators that are behind the horizon, and this is a problem to understand it. So I know I was being vague in my assumption, in my affirmations. It's true. You're right. But what I wanted to say is that it doesn't seem that entanglement entropy by itself is gonna fully characterize the geometry in gravity when at least when there are horizons present. So one question that we could ask ourselves is there any other measure of entanglement that is able to do the job? Is there any other quantity that could enter into the black hole for long times and let us explore the interior of the black hole? And what it has been speculated is that maybe quantum complexity is the right measure of entanglement that does the job. So even defining quantum complexity is kind of a nightmare. You could write books and books about quantum complexity with different definitions, and even you wouldn't find decent definitions for continuum quantum field theories. So what I'm gonna do here is just do basically what Saskin did, which is to use a very cheap definition of complexity, which is based on the idea of tensor networks. So tensor networks is just the idea that if you have a Hilbert space, okay, like this one, you can always choose a partition of it in qubits, for example, or something more complex if you want, but just partite the Hilbert space in a number of smaller Hilbert spaces, and then you can always express any state in this Hilbert space as a bunch of coefficients in the basis in which. So sorry, maybe I'm skipping some of the details in case you don't know this, but these elements here are the basis of each of these Hilbert spaces. These guys span each of these small Hilbert spaces, and then every state is expressed just as a tensor with has n coefficients if we have parted the Hilbert space in n pieces, and that has some exponential number of coefficients that specify the state. Okay, so there's a pictorial way of drawing this, which is that to think about this tensor as this blob which has n legs, and since, for example, if we have chosen to partite our Hilbert space in qubits, which have only two degrees of freedom, then this amounts to a quantity of independent coefficients of this tensor of 2 to the n, right? The idea behind tensor networks is that for reasonable quantum field theories that are local and so on, really most of the states that are interesting, most of the states that can be prepared by acting with simple operators from in the vacuum and let them thermalize and so on, the whole set of states that are interesting for physics are really a very small set of states in the whole Hilbert space. What do I mean with this? What I mean is that you don't really need to specify 2 to the n coefficients if you want to talk about states that are physical. So the idea behind this is that one could take this tremendous object, this 2 to the n coefficients tensor, and just approximate it by a bunch of smaller tensors which have some properties that you can fix ab initio, and then contract them themselves by forming some kind of structure. This reduces the problem of specifying 2 to the n coefficients to a problem of specifying some polynomial number of coefficients. This is what we call a tensor network, and it has been very useful in many fields of physics, such as, for example, condensed matter systems. It has been used also, for example, to compute, basically to do some versions of the conformal bootstrap with tensor networks and fix the coefficients of some conformal theories, real conformal theories. And it's just a tool that people use that is really successful in finding, for example, grand states of local Hamiltonians. So this is an approximation, of course, which is just approximates the true state that we want to find by some epsilon. But once you're given this epsilon and you really find the minimal tensor network that does this job of approximating the state within this accuracy, then you can define the complexity just simply as the number of tensors that you needed to do the job, right? So in this case, we needed 1, 2, 3, 4, 5, 6, 8 tensors, right? And the complexity of this state, we would say within a given epsilon, we would say that it's 8, because it's the number of small tensors that we needed to approximate the state within some accuracy. Okay, so this is some cheap definition of complexity, and what is inspiring about this definition is that if one goes to conformal field theories now, one can learn.
Ask, Javier, so can you go back? So
yeah, sure.
So these coefficients are not chosen from the same set. So for example, it's just a 3 index matrix, no?
Mm-hmm. For example,
so,
yeah.
So it needs 2 to the 3, 2 to the power.
Yeah, so it's polynomial in n times 2 to the legs. Yeah.
So here the complexity would be related to the number of indices, alpha, beta, the number of indices you add. Or is this just fixed?
Okay, so the idea is okay. Good question, but So the idea is that you give, so the reduction from exponential to polynomial number of coefficients means precisely that there is a polynomial number which is the number of tensors that I used, and then there is an exponential which is 2 to the number of legs of its tensor network. What I'm doing here is just to neglect that. So usually what you do is you take your basic building blocks, which are these small tensor networks, as being tensors with few legs. How many you want? For example, you can take 5. And then, of course, the complexity would be 2 to the 5 times the number of tensors, right? But what I'm doing here is just forgetting about this 2 to the 5, which is just some global normalization, if you want, and just count the number of tensors. So if you do change, of course, if you do change the number of legs or even how many indices these legs run, for example, I could use, instead of qubits, I could use qubits or qubits in general. What people in complexity theory prove is that this really never changes things. So the important thing here is the complexity class. So this is like in quantum computation, for example. Let me define complexity, for example, as the number of gates that you need to use in a quantum computer to perform some computation in a quantum circuit. Of course, the exact number of gates depends on whether you choose a universal basis that has the Toffoli gate or not, right? Because the Toffoli gate is a 3-qubit gate, and other gates like the Hadamard are only 2-qubit gates. But the assumption here, or even the proof sometimes, is that if some problem is in some complexity class, the choice of gates is not going to change that by more than maybe another one factor.
Okay.
Right. So in this sense, choosing different tensors in this definition would change another one factor in the overall behavior of complexity, but would not change other things, such as, for example, how fast it grows in certain procedures and so on.
Wait, another question. So apparently, in the example you are quoting here, apparently you need n tensors. So exactly as in the original state. So how can
in the original state I used one tensor that had 2 to the n coefficients.
Yeah, no, that I understand. But,
okay.
But you said that complexity is the number of dots in Tn. So
yeah.
how the number of dots on Tn could be lower than n? Or can it be lower than n? Because apparently...
okay, no. Well, it was just a picture. Sorry, no. So, I mean, if the number of tensors is very, if you only use one tensor, probably you have to use a very big one, such as the first one. Yeah. So this is a picture. I'm sorry. Usually there are at least n tensors in the game, of course.
Okay. So
usually more. So for example,
so the complexity is, let's say, there is a lower bound, which is n, or
yeah, sort of, but. Well, but this also depends on what is the kind of tensors that you allow to use. You allow yourself to use at the beginning, right? Because I mean, if you use, for example, in this first picture, this you could call this a tensor network with only one tensor, and you could say the complexity here is 1, but you're using a pretty big building block, so it's not reasonable. So the point of view here is that you take simple building blocks, which are small, that have few legs and few coefficients, and then see how well can you do in approximating the state with the minimum number of them that you can. But it is true that people who really use this stuff never use tensors that are smaller than n. So, for example, when people who compute things in conformal field theory in 1+1 dimension, they usually use MPS, matrix product states, which are tensor networks, which are basically a line. They are ... and then joined by links and with some vertical links, and they use complexity that is equal to n, basically. But for some other things, you might be interested in bigger numbers, such as, for example, just taking, well, you will see an example of that in a minute, which is, for example, the MERA, in which you use more tensors, but you use them in a clever manner so that the result is more efficient. Sorry, maybe I'm not explaining it myself very, very good. I'm feeling that, but
no, okay, go on.
Okay, so so here there's an example of what you said, right? So when you go to conformal field theories, it turns out, and this was proved by Guise in 2006, that the tensor networks that are most efficient to describe conformal field theories have a geometry that is hyperbolic. Okay, so this is well, my drawing is really bad, but you can look this term up on Google and you will see nicer pictures. So there is this tensor network which is called the multiscale entanglement renormalization ansatz, which has this form. Okay, the physical links, so the links that go to the qubits would be those dangling legs that are here. Oh, sorry. And then there is a whole structure of tensors that one builds that has hyperbolic geometry. Okay, so in this case, for example, it is obvious that we have a number of tensors that is bigger than n, right? Because the number of legs here, there is at least one tensor for each, but then there are a lot more in the middle. Okay, so Guifré Vidal is a guy who works in just condensed matter systems, so he was not very interested in holography. He just realized that this was a useful ansatz to calculate things. But then there were some people that stared into this tensor network long enough as to realize that this looks like a slice of ADS3. And this is very inspiring, because since you're describing a tensor network for a conformal field theory, then it could suggest that the space of tensor networks is somehow recovering a discretized version of a spacetime, right? This was proposed by Brian Swingle in several papers, where the renormalization group that acts on the tensor network, it was interpreted as the holographic renormalization group, and so on. And this led Leonard Susskind to the proposal that if one thinks about these tensor networks as being a discretized version of the emergent spacetime description for the conformal field theory, then one could define the complexity of these tensors just by computing the volume of these slices, right? Since this is a slice, a fixed time slice of ADS3, the number of tensors that one can count here is just the volume of this guy, well, multiplied by the discretization scale, which is the ADS radius, right? So the proposal of Leonard Susskind in a paper in 2014 is that maybe volumes, instead of areas, as the Ryutaka-Yanagi formula suggested, could be useful to characterize the complexity of a state. Of course, you have to normalize this by appropriate coefficients. You need to put here a factor of G Newton and then some arbitrary scale. And you could get this number, okay? Where inspired by the Ryutaka-Yanagi proposal, Susskind proposed that the slice that we should pick is not a constant time slice in general, but in more complete situations, it should be some extremal codimension one surface. Okay, so just as in Ryutaka-Yanagi areas happen, but with 1 unit more of codimension.
Javier, just a yes/no answer. Very simple. Is there, at least in principle, a generalization of this picture for higher dimensions, or this is just simply tied to ADS3? So I mean, can you only connect this to
the MERA? You mean the MERA?
I mean, can you make out of this, instead of this one line border, a surface and then a real volume inside? Is there a picture, yeah, with MERA that makes
MERA,
sense?
so you can build MERAs in higher dimensions, yes.
Yeah. No,
so
but
I cannot. The problem is I cannot draw them, but you can build them. You can build them. If you ask the quantum the condensed matter guys, they will tell you that they don't like higher dimensional meras because PEPs are efficient enough in higher dimensions. I don't know if you know what are PEPs. So PEPs are another family of tensor networks that are called projected entangled pair states, which are basically lattices, right? They are square lattices.
Just a simple question. The question is whether how much of a coincidence was this to happen in three dimensions, or whether this at least could make sense. I mean, just to extend from ADS to any ADS.
I mean, this whole business, I admit, is very flimsy, and it's based on very loose conjectures by Susskind, who, you know, is kind of crazy. But this in particular, I think you can do it in higher dimensions too. So whether the 3-dimensional or 4-dimensional mera is the more efficient description for a conformal theory in higher dimensions is something that has not been proved. So mera is usually only used in 2 dimensions, but because most of the papers on tensor networks are only in 2 dimensions, because 3 is very hard. But you can construct 3-dimensional meras, and they could still be interpreted as slices of an ADS4.
Okay, go ahead. Otherwise, you won't finish today. Yeah. Okay.
It's okay. I don't mind not finishing. It's all right. Okay, so this proposal by Linus Susskind means what it means is that to calculate the complexity of some state or some holographic state, what we are instructed to do is just to compute these streamal slices, which, for example, in the case of a black hole, look like this. Okay, so there are slices that at time equals 0 just cross horizontally the spacetime. But then as time goes by and one evolves, the 2 times have the 2 boundaries, right? Because the boundary conditions are that you anchor these surfaces at both sides. They saturate in some maximal surface that they cannot pass in such a way that this volume grows linearly with time. So a way to see this that is better is to draw the same picture in Eddington-Wittgenstein coordinates, okay, where the singularity would be this vertical line and the horizon is right here, and there is a constant R surface that lies in the interior, which is in which the volume functional maximizes, and these slices that are maximal and are anchored at the boundary. What they do is basically they go horizontal here, and then they enter into the black hole and they saturate on this surface. So here is very easy to see that the length of this surface is basically grows linearly with time. There's nothing more than that. And this actually recovers the phenomenology that you would expect from complexity, right? From the quantum mechanics point of view, which is that complexity grows linearly for exponentially large times. Okay, complexity is a quantity that can be very, very large. Okay, it's really quantum complexity is really different from classical complexity, because there are a lot of coefficients that need to be specified, that can be specified to determine to fix a state in Hilbert space. So Hilbert space is huge, and we expect that any state that evolves under some generic Hamiltonian, under a chaotic Hamiltonian, a sufficiently chaotic Hamiltonian, should have a complexity that grows for exponentially large times. So I don't have time to build more intuition about that, but recently I found that maybe there is an example of classical complexity that is kind of simple to understand, which is the Rubik's cube. Okay, so imagine you have a Rubik's cube, and you want to know how hard it is to solve. Okay, so the Rubik's cube has something like 20 trillion configurations. Okay, and you want to turn it back to the initial state. So the complexity of the Rubik's cube at some given position is given by how many turns that you need to do to go back to the original position. Okay, so what we call simple operation here would be to make a turn in the Rubik's cube. And it has been recently discovered by mathematicians, and surprisingly, just a few years ago, that there is a magic number, which is 20, which is the maximum number of turns that you have to do to solve a Rubik's cube. Okay, So then you could ask how many states are that far, and how many are closer to the original state. And if you draw the number of configurations that have, and you classify all the configurations for its complexity, meaning for its distance, its minimum distance to the original state, you will see that they grow exponentially. So if you take a Rubik's cube and then which is solved, for example, and then you do random turns, it's almost impossible that you will go back in complexity. You always go, since every step, steps that have bigger complexity are exponentially more than states that have a smaller complexity. Any random turn of the Rubik cube would go to the maximal complexity, okay, linearly. Basically, all the turns that I do, if they are random, they increase the complexity of the cube. This is more or less what happens here. So every time that the Hamiltonian acts on these states, their complexity generically grows until it reaches its maximum, which is some saturation. And then, so in quantum mechanics, this maximum is much bigger because it's exponential in the number of configurations instead of linear. But then it usually stays there until some Poincare recurrence occur. Okay. I don't know if you followed my explanation. I don't know if okay, if there are no questions, I'll go further. Okay, so one could also ask about the complexity of operators, okay, which is something similar that I just explained. So imagine we have a toy model, for example, based on some chaotic k-local Hamiltonian with where with k-local I mean that it can be modeled by a quantum circuit in which the gates act only on few qubits, on k qubits in particular. Okay, that's what people mean with k-local. This doesn't mean that the Hamiltonian have to be physically local in the sense that it only acts on qubits that are physically next to each other, but it does mean that the Hamiltonian cannot act on qubits on many qubits at the same time. Okay, so for example, the SYK system would be sort of a 4 local Hamiltonian because the interaction term involves 4 fermions, and this is what we could write the evolution under this Hamiltonian as a quantum circuit with 4 qubit gates, for example. Okay, so when one takes these kind of systems and one wonders what happens with an operator that we insert in this in a state that is evolving under this Hamiltonian, the typical answer that one gets is that the size of this operator, meaning how this operator affects the whole state, grows exponentially with time. Okay, this is getting this basically comes from validating some epidemic model, which unfortunately we're very used to this year. So we all know how this works. So the idea is that I insert an operator here, and then I let the state evolve under the unitary operator, and this operator will grow as it hits the gates in the quantum circuit. Okay, since every time it hits a gate, this will at least duplicate. The growth of the operator will be exponential until it reaches the size of the circuit, which is fixed by the entropy, and then it saturates. Okay, so this is the typical behavior of an epidemic model where this lambda coefficient that controls the exponential is called a Lyapunov exponent. It's the same Lyapunov exponent that you can find, for example, in OTOC correlators. And this has been studied, for example, in the SYK model has been studied in many papers in detail, even computing this Lyapunov exponent. And there are some conjectures, for example, that whenever one has models that are maximally chaotic, that have, for example, that have a gravity dual, then this Lyapunov exponent is bounded by this value, which is 2 pi over beta. The SYK, for example, is an example in which this Lyapunov exponent is saturated. Okay, so related to this operator growth, there is this whole idea that gravitational clumping. So the question would be what all this means in the gravity side. So there's an old idea that gravitational clumping must increase complexity. Okay, so for example, it was mentioned already in the original paper by Saskin in 1994, and it also has been suggested by Berlinde that gravity, all these ideas that gravity might be an entropic force and so on, because falling in the space-time picture seems to increase the complexity of the conformal field theory. For example, in modern terms, if one thinks about bulk reconstruction procedure, for example, if one wants to write a bulk operator in terms of boundary operators, the standard result is that if this operator is close to the boundary, then you can write this operator, this bulk operator, as a bunch, as a small bunch of local operators in the conformal field theory. But as this operator falls into the interior of the spacetime, then the region in which the reconstruction is supported gets bigger. In this sense, the operator becomes more and more complex, and this is related to this particle falling towards the center of the ADS. So these ideas are very vague, and they were extended somehow by Leonard Susskind a couple of years ago to maybe more vague things, but which is the following. So in some papers, Susskind proposed that there is a size momentum correspondence, meaning that this sort of exponential growth that one sees in these epidemic models for operators that are inserted and then in a state and then evolved under a chaotic k-local Hamiltonian, this would correspond to a particle falling towards the horizon in the dual gravitational theory. Okay, so if one takes, for example, a particle falling through a black hole and then studies it in the Rindler frame, it's easy to see that indeed the momentum, the radial momentum of this particle as it falls to the horizon behaves exactly like this operator is believed to behave. Okay, this momentum goes like the exponential of lambda over t, where lambda is the correct Lyapunov coefficient, and we're computing the radial momentum in Rindler coordinates, and t is the asymptotic boundary time. So in this paper, Lenny proposed that maybe this growth of the size of the operator, this ds dt, would be given by the radial momentum of the particle that infalls in the black hole.
Sorry, Javier, you say you're computing this in Rindler time, but I see just in Codazzi time.
No, so you compute. So what he does in the paper is to compute the radial momentum in Rindler coordinates, and then translate and then change variables to the coordinate in the boundary. So this t here, is really the asymptotic coordinate. It's not t Rindler. Okay, it's this t.
So then you have to go through Rindler coordinates. If in the end you're going to express this in
well, just to use the coordinate rho.
The coordinate what?
The coordinate rho, which is the one, which is this this particular foliation of this particular spatial coordinate.
Right. Okay.
Okay. So this is kind of a crazy proposal, and it could be a coincidence, but it's true that in a later paper he performed together with more people a more precise check, which was to consider some near extremal Reisner Nostrom black hole and study this proposal of what happens with the momentum of an infalling particle in a near extremal black hole, and then compare the result to the SYK model. And incidentally, there were a bunch of papers by Key and Streicher and by Roberts, Stanford, and Streicher who computed very precisely what is the growth of operators in the SYK model, and they found a bunch of functions. Sorry, and they are not so simple as this one. They are complicated things with hyperbolic signs and so on, and some Fish coefficients. And surprisingly, this proposal holds. So really, the momentum does behave like that. So the momentum of an infalling particle, it seems to recover the same function as the growth of the size of operators in the SYK model before scrambling, right? So this is so the procedure. This procedure of the infection is basically an scrambling procedure, and also this particle falling into we know that the scrambling in the dual gravitational theory correspond to what particles do when they hit the stretch horizon, right? So I don't know. It was it's still kind of a crazy proposal, but it was curious that he was able to even to get the correct coefficients for the SYK model.
Javier, is at least easy to see from this picture that the stopping, I mean the saturation?
No, you don't see it. You don't see it.
Okay.
You don't see it. So this is believed to be this is a picture that it's only right for until the scrambling time.
Okay.
I agree. So what our proposal will go to the black hole interior. That is what we did. Okay, so exactly. So what happens after scrambling? Okay, so the size, obviously, the size of the operator has to reach some finite size, which is set by the entropy, and the size should stabilize. Okay, should be aligned like this. However, complexity should be growing still, because of what I said before. Complexity is way bigger and should keep growing for exponentially large times. This is sort to say that even when the operator has achieved a size which is bigger, which is the same size of the circuit, there's still a lot of combinations of gates that you can still add, and this will increase the complexity. In order to see this concretely, you should. There are some proper definitions of complexity that you can look up. For example, there is a paper by Barbon and Rabinovici and collaborators from last year, which proposes a particular measure of complexity, which is called Krylov complexity. It's basically a measure of the number of nested commutators with the Hamiltonian that you have to do to approximate the operator, and they do find this behavior that is expected from complexity, that it grows linearly with time after scrambling has happened. Okay, so if this proposal that Saskin came up with is to be valid also in the black hole interior, then this complexity equals momentum correspondence should be frozen after the T scrambling. What I mean with this is that since C dot it's a line here and it's just linearly growing, then the momentum inside the black hole should be something fixed, which is rather odd. It really there is really not much hope that there will be some notion of momentum inside a black hole interior. In which the momentum is constant, right? Because whenever you throw a particle into a black hole, this will accelerate, and at some point it will crash the singularity. But it's really hard to think that anything is going to be constant in there. But as we will see, it does happen. Okay, so what we did in our papers is just to propose some momentum complexity correspondence that is completely general, and that is covariant, and that recovers the correct phenomenally. So our goal is to derive a proof of this C dot equals P. And for this, we need to define what is P, because there's a lot of freedom in defining a momentum. So our assumptions are going to be very easy. We're just going to assume that we have Einstein gravity and matter in the bulk, plus maybe some decent boundary conditions. So in general, we will assume that we have some asymptotically killing vector, for example, that time is a killing vector in the boundary, but we don't even need to assume that we're on ADS space, because it will also work on flat space. And we're also going to assume this volume complexity prescription, which is what I told you before, that the volume of some state can be approximated in holography at leading order in 1/n by the volume of some extremal codimension 1 slice. So in that sense, we could approximate, for example, one way we could compute complexity of an operator would be just to compute the complexity of the state that evolves under this operator and subtract the complexity of the state of what would have happened with this state if we had not inserted the operator. Okay, but there are a bunch of questions that we need to answer here. The first one is, the most important one is, what is exactly P? Okay, Susskind's notion was not very covariant, right? He just randomly took some momentum, just that he took some derivative of a radial momentum in some coordinates that he came up, and then he chose to express that in some random time too. And this is not very serious, right? It seems like he chose it as a coincidence, right? So we need to make a couple of choices that make this decision more covariant. So we need to choose a time variable, which is the same as to say that we need to choose a foliation of a spacetime, which will determine what is the momentum that we're measuring respect to which time we're measuring momentum. And we also have to choose a momentum component, right? Because this is a scalar. He was choosing the radial one, but there is no reason he can do that in general. So we need to choose some component which is tangent to some direction tangent to the slice to this foliation, so as to select one interesting component of the momentum. As we will see, this is going to be related with some radial kind of component, so that it measures infall momentum, but we will see. Okay, so what is the question of what is the answer to the first question? What slicing should we pick? So we said that in order to recover the phenomenology that we want, which is that complexity grows linearly after scrambling time, which corresponds to the black hole interior, we need a notion of momentum that freezes after scrambling. So we need something. We need a time foliation in which the momentum remains constant when the particle goes inside the black hole. And it turns out, if you stare at these maximal volume slices long enough, you will realize that these are actually a good candidate for that. These extrema slices are covariantly defined, right? They're not a random choice. We're choosing to foliate our spacetime with maximal slices, and they do exactly this job, which is that when one measures the momentum respect to the time coordinate at the boundary, this momentum becomes freezed in the black hole interior due to this accumulation of slices before the limiting surface. Okay, so there is a notion, there is a momentum density that we may define from the energy momentum tensor, which is the momentum measured with this time foliation, which is just obtained by taking the contraction of this energy momentum tensor with the normal vector of the slices. Okay, this n maybe should have a subscript sigma here, where n is the normal vector to the slices. And also we have to select what is the momentum component. So we need to take some other field, okay, with which to contract this momentum density with, and then integrate over the slices. Okay, this is going to be a vector that lives that should be tangent to the slices, but a priori we have no reason to choose one or another.
Javier, just to say that you essentially still have 10 minutes left.
Okay, then I'm going to skip a bunch of stuff, and that's all. Okay, so what we did is to prove, just using general relativity techniques, that there is a choice of momentum that does recover this complexity growth as defined by the volume. For those of you that don't really believe in this complexity business, which is totally fair, it's also nice that we found some relation between a notion of infall momentum and just the growth of volumes, right? This is kind of similar actually to what people has done, for example, studying how the entanglement entropy, as given by Rubik dynamic formula, evolves under generic variations of the boundary conditions. Here, instead of a codimension 1 surface, we have a codimension 1 surface, and what we were able is to parameterize the growth of these surfaces as they evolve in time, just as an integral over some momentum in the bulk. Okay, so The answer is, so the question is, can we do this more generally? And this is the computation would follow these lines. So since these surfaces are extremal, variations of the volume are just a boundary term. So we can write the derivative of the volume dv dt as just a simple boundary term just that is evaluated at, in case we're an ADS at the ADS boundary, but we can also put some fixed box in flat space and then compute volumes that are anchored on this box. So since this is a boundary term, the trick that we used is that we can define a current that has exactly the same value at the boundary, but that can have whatever value that we want in the bulk. Okay, as long as the value at the boundary is the same, this will be the correct result for V dot, and then we can use the Stokes theorem just to write V dot as an integral that is now not on the boundary of the slice, but as an integral over the slice, where now, of course, we have to introduce the derivative of the current. So now what we have to do is to find a clever choice of this current that contains a momentum. And there is an obvious answer to this, which is that we can use the momentum constraint. The momentum constraint is just a constraint equation of general relativity. It's kind of a Gauss law for general relativity, which is a relation of positions of momenta that is not a dynamical quantity, but just a constraint that the theory has to satisfy. There are four of them. There are the three components of the momentum constraint and what is called the Hamiltonian constraint. So this is the momentum constraint, the famous momentum constraint, where we can eliminate this term because these slices are maximal, and accordingly the trace of the extrinsic curvature vanishes. And this notion of momentum that I'm writing here is basically the one that I proposed before, right? It's just the energy momentum tensor contracted with the normal vector to the slices, and then we project it to the slice, so that since this indices run only through the dimensions of the slice, we have to project it with these standard vector fields. Okay, so the momentum constraint gives us a notion of momentum, but we still need a scalar, so we need to contract with some other vector field and then integrate to get some finite quantity, to get some scalar quantity. Okay, so we can do that. This notion of momentum would be precisely that, just this density contracted with an arbitrary vector field and then integrate it over. And then the trick is just to choose Rj as to be this term here. Okay, we have used here some manipulations to write the integral again as a boundary term plus a term over the slice. And if we take now J to be of this form and fix C by the boundary conditions that we need, so that J has the correct boundary conditions, we almost get what we were looking for, which is that we can write V dot as some momentum, right? Where this is an integral over an energy momentum tensor contracted with the normal vectors and some C field plus a reminder. Okay, this is, well, actually I have here, this would be our C infall momentum, and there is a reminder here that we don't know how to deal with. So this would have been a success if we hadn't found a reminder, but we did. So how do we get rid of this reminder? So can we? Actually, we can. Okay, we can rewrite this reminder in such a form that it can be written just as a Lie conformal derivative of the metric, so that we can also set this reminder to 0 if we would choose C a conformal Killing vector. Okay, if C is a conformal Killing vector, then V dot is just exactly PC, and we have this our momentum complexity correspondence or our volume complexity correspondence, if you like. Okay, this actually can always be done, for example, for all spherically symmetric states in any dimension, and in general for any states in 2+1 dimensions. For example, for spherically symmetric states, there is there is indeed this conformal Killing vector, which is given basically by the radial vector that it's inward pointing, and that has some particular normalization given by R. So it's basically the radial vector, but with a normalization that depends on the position of the radius. So this is nice because we did manage to prove that there is a relation between momentum infall and the growth of volumes. And actually, the vector that we obtained was precisely an infall vector field in the sense that it's radial, it points to the center, and give us the correct result. So I said that for spherically symmetric states, we can also always find this vector, also in 2+1 dimensions, but in general, this is not true, okay? In particular, if there are gravitational waves, there's not always possible to get rid of this remainder, and there might also be some topological abstractions. So there's one reason, there's one way it's very easy to see that the gravitational waves cannot make the remainder equal 0, which is that if we have a solution that is purely made of gravitational waves, this has T mu nu equals 0, but they do deform the spacetime. So it would be unreasonable to expect that volumes are not gonna change when we put a bunch of gravitational waves in our spacetime. In particular, we could even form black holes by just collapsing gravitational waves, and we would get a volume growth that is non-zero. So this remainder must somehow codify what gravitational waves do. So this is what we did in the next paper, which is just to rewrite this remainder in a way that explicitly codifies what gravitational waves do. So what we achieved is just some generalized momentum complexity correspondence, as we call, in which we're able to write the rate of growth of volumes as a sum of two terms, where one is the one that I showed you before, which is this infall component of matter momentum, but there is another contribution which we call W, which is basically some gravitational momentum computed from the Weil tensor. So we know that in the Riemann tensor can be decomposed in the Ricci tensor and the Weil tensor. The Ricci tensor is always related to the energy momentum tensor of matter by the Einstein equations, but the Weil tensor usually contains all information that is related with gravitational waves. So what we did here is to write explicitly this variation in a way that isolates the term that is provoked by the matter energy momentum tensor and some other component that we can interpret as some gravitational momentum. In this case, instead of an infall vector, we have to define a bigger object which has three indices, and that we don't understand so well, but we were able to. Sorry, did we? Oh, I thought someone was talking, but we were even able to check this formula in an explicit example. So we found some simple enough solution of a PP wave, which basically it's some infinite plane wave, an infinite gravitational plane wave, and we managed to study this system from 2 points of view. First, we were able to obtain a calculation by means of a non-cell procedure, so just taking the volumes and calculated them explicitly, and then taking derivative with respect to the boundary conditions, and then we were able to obtain the exact same result using this formula, right? That the volume is given by these two contributions, and then interpret this second one as some gravitational momentum, where actually we were able to find a version of the Bell-Robinson tensor, which is something that has been proposed before as a measure for gravitational momentum. Okay, since I don't have much time, and I think I did it pretty badly with the time and, well, in general, but so I'm going to jump to the conclusion, which is that we managed to prove that there exists a notion of infall momentum in such a way that C dot equals P, right? Which works for spherical states in any dimension, works for any state in 2+1 dimensions. It's exact, it's covariant. It has the desired property that gravitational clumping increases complexity, and it's also valid in black hole interior. Okay, but the previous proposals, apart from being pretty ad hoc and not covariant, were not able to compute the complexity growth in, after the scrambling time, and we think this is nice. We also generalized it to more complicated spacetimes which have gravitational waves, where we have an extra time which could be interpreted as taking care of gravitational waves via some sort of infall momentum for gravitational waves, and we were able to check it in an explicit example, saying that it works. So there are some open questions, of course. As I mentioned very briefly, we don't really have a geometrical meaning for these three tensors that we have to introduce in order to take into account for the gravitational waves. It's sort of like a bigger version of the infall field. So we do not know if this infall momentum of gravitational waves is a correct interpretation. As you know, momentum is not really defined for pure gravity. The best you can usually do is to define it perturbatively via some lambda-Lipschitz tensor or something of that sort. So it would be nice also to see if perturbatively we can obtain, for example, this lambda-Lipschitz tensor in some calculation. And there are many other questions. For example, there are some proposed first and second laws for complexity, which might give bounds for the growth of complexity, or even the second derivative of complexity that have been proposed by Myers and collaborators. And also this could lead, for example, to relations between complexity and the energy conditions. So in a similar fashion as what happens in entanglement entropies, in which variations of entanglement entropy have been shown to be linked to the existence of null energy conditions, for example, in some papers by Aaron Wall and Hartman and some other people. Maybe it could also be that these volumes have such property that they're postulating some positivity bounds for the growth of complexity, or volumes could lead to relations with energy conditions in general relativity. Okay, so I guess I'm out of time, so that's all.
Thank you, Javier. We can all unmute and give a round of applause.
Sorry, I